He's on.
So this is
Mhm. And this camera's gonna point to this room. If somebody comes, they sit over here. That's about it.
so we're seeing the chances actually.
I just even get out of there. I find it a lot easier to do the settings in the Zoom itself than. Yeah, check this. And this sometimes doesn't work. And we're good.
Is there any for the rest of the day?
Statistics at 1 or 12. There's Tom scales at 8 and 12, the young is 12. Christy Lowry at 1:30. Frank Ritchie right here at 1:30. Where at 1:30, so there's a bunch at 1:30, young at 1:30. I know Sullivan. So we so anything in Anderson, Anthem is all Zoom. Where is Zoom? In Young is Zoom. And O'Sullivan is always Zoom. Okay, easier. John Patrick isn't Zoom.
Okay, so.
I do. That's awesome. Oh, thanks.
I was gonna do some cheesy eggs.
Wow,
Yeah.
that's good. I'm hungry. Cool, thank you. I'm used to making my own breakfast, and so I think it's really, really sweet that he just wants to let me like sleep a little longer, you know, just get ready and not rush. Then I get to come downstairs to breakfast being made for me and coffee and all that good stuff. So it's just really sweet.
Sure. You want to cut some bread.
Yeah.
Get some of that awesome bread last night.
Hello.
Awesome.
Good morning. Is this Miss Ray?
Yes, it is.
Hey, this is Evan. I'm going to put it for your son.
Yes.
Okay, perfect. Is now an okay time to do that for? All right. And he was referred to us by an officer.
So
Okay. And do you know who he saw at Aspen?
I got the paperwork. Hold on. Ooh, Let's see. Hannah. And then the last name is Anki.
Okay.
Yeah.
And did they let you know which tooth it is that we need to
Yes.
look at for him?
It is the number 30 is the one giving him the most problems.
Okay. And is he having pain on that tooth?
Yes.
Okay. Do you know where he put that on a scale of 1 to 10?
Most of the time I think it's about a 9 and a 10 when it starts. Because he'll be crying.
Any sensitivities to hot, cold, or pressure that he's mentioned to you?
Not really. It seems like room temperature water is the best thing that he does for it. He doesn't seem to try to eat on that side, and he tries to keep it on the other side, you know, if it's hot or if it's cold.
Okay. Any swelling in the gum or cheek around that tooth?
No, they said there was none.
Okay. Has that tooth had a root canal at all before?
No,
And did Aspen give him any antibiotics for it?
No.
Has he taken anything over the counter?
Yeah, he's taking some Advil when it acts out.
Okay. So that discomfort's kind of off and on
Yeah.
for him?
Mm-hmm.
Okay. And how long has that been going on for him?
Since the beginning of October.
Okay.
And I've been calling around trying to find people. You know, they gave me a list of different types of, different people, but it's hard to find somebody that will do a root canal on that number 32.
I gotcha. Okay. All right. And what is your son's first and last name?
His first name is Dale, D-A-L-E. Last name Moody, M-O-O-D-Y.
Okay. And his date of birth?
9/22/2010.
All right. Let me take a quick peek at my schedule
Okay.
and see when I can get him in.
Okay.
Do you have a
Hey,
preference?
Nicole, I don't know if you know, but we can hear you.
I mean, I'll find out wherever they're at. I know
Nicole.
Midlothian because me and my husband go there quite a bit, but a short pump's not that far from that, is it?
No, Short Pump's about 20 minutes from the Midlothian
Yeah,
area,
so-
and then the Mechanicsville location is 20 minutes from Short Pump.
Yeah, it doesn't matter at that point.
Okay.
Nicole, can you mute your
Well, bear
mic?
with me 1 second.
That's
Let me
fine.
pull both of the schedules for you, and I will
Okay.
get him set up soon.
All
Okay.
right, thank
Nicole.
you.
I'll be right back for you.
And they do realize he's 12, right?
Nicole.
I don't want him, to
I
get
know.
there and then say, we don't do kids.
Right.
Hey, everybody.
Hello. Hi.
Let's see. I am muted. Sorry, my sound is muted. There we go. I should be able to hear you now.
Hello.
Thank you. Hello. Let's see. I wanted today, the big thing I wanted to do today is go through that. There's only one homework assignment for this module. And I went and checked through the test since last class too, to make sure it lined up with the homework assignment. So if we can get through this homework assignment today, it may be Wednesday, you should be ready to take the test. And the test isn't bad. We talked a lot about a lot of things in this module. and not all of it lands on the test. So don't be too intimidated. A lot of it is just a discussion to learn some stuff about some topics. So let us see. Here we are. And here we are. I got all this stuff up, but sorry, the order is not as pretty as it should have been. I have a little trouble reordering these things on a tablet. On my laptop is pretty easy, but I'm sure there's a way to drag these things, but I can't. I don't know. But anyway, it stops up here with the fourth video, and then I added the fifth and sixth, and they showed up down here. So sorry about that. A little bit out of order, but the test is still at the bottom. You see the due date's November 6th. I didn't want you to have to rush on that. There are a few of these problems I want to look at from the class practice too. So we'll do those, and then we'll get to this homework assignment and work through those together. It's a lot of arrows. Excuse me. So let's just look for a second at some basic counting rules. Because sometimes when we do probability, we need to know how many outcomes there are in a sample space. We may not even need to know what they look like, but we need to know how many there are, because when we calculate probability, the denominator in that probability is always the number in the sample space. And we kind of ran into this without discussing it too much when we were talking about having children and doing a tree diagram. We had the Ritchie family had 3 kids, and the first child, it's pretty much equally likely to be a girl or a boy. Then our second child, okay, we had a boy first in our family, but of course, that's just our family. And then we had equally likely chance of having a girl or a boy with the second child. My tree diagrams are atrocious, I know. The ones on the quiz look a lot nicer.
I
So
think that was pretty nice.
Yeah, trees don't have 3 branches anyway.
Yeah, I think it looks great.
Thank you. This one's really going to be a squeeze. Okay, here's my third child. And it was equally likely to have a girl or a boy on that third one. So in the end, we had how many different outcomes? Let's see. And we just kind of labeled those at the end of each branch. This one was girl, girl, girl. So I just wrote girl, 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 and then girl, girl, boy. And then girl, boy, girl. And this tree diagram, make sure we get all of them and don't duplicate any. Girl, boy, boy. And then boy, girl, girl. Boy, girl, boy. Boy, boy, girl. So how many different outcomes did we end up with here? You count these outcomes at the end of these branches.
8.
Yeah, 8 of them. All right. And we had 3 events here, and each one had 2 possibilities. So this one had 2 possibilities. I could have a girl or a boy. And then the next child, I had 2 possibilities, a girl or a boy. And then the last one, I had 2 possibilities, a girl or a boy. And ended up with 8 different outcomes. So how could I have calculated that? Like if I wasn't worried about the G's and the B's, and I just wanted to know how many at the beginning of the problem, you say, okay, Brent, you're having 3 kids, 2 possibilities each time. How many total outcomes at the end of it? How could I have done that without drawing all this out? Looking at these numbers I've written here. What arithmetic operation could I put between those 2's? So at 2 something 2 something 2, it would equal 8.
Multiplication.
Yep, there you go. So it's as simple as multiplying. If you have 2 outcomes and then another event with 2 outcomes, and then a third event with 2 outcomes, then you have 2 times 2 times 2, which is 8 outcomes to the whole compound event of having 3 children. So it really saves time if you have, we have friends that have 6 kids, and I'd hate to do a tree diagram for 6 children, but you could say, well, I can at least figure out how many outcomes there are by doing 2 times 2 times 2, 6 times. Or if you're using a calculator, you could just do 2 to the 6th power. 1, 2, 3, 4, 5, 6. And make sure you multiply. People fall in the trap of adding these things. That's 4, 8, 16, 32, 64. So if I had attempted to draw that tree, at the end of it, all the way out on the right, I would have had 64 outcomes in the sample space. So this is a quick way to answer the question, how many? Now, it doesn't show us specifics. If you come back and say, well, how many of those 64 have exactly 3 girls in them? Well, then you're going to have to do a little work to figure out how many have 3 girls in them. But a lot of times you don't need to know that. You just need to know how many total. And this is a multiplication rule for counting. And it works in a ton of cases, so that's nice. When we find are asked to have a PIN with our bank card, used to be there were four digits. Now there's so many different ones. But I know on my iPhone, I have a PIN on the lock screen. And there are 4 digits. Now, how many in our number system, how many digits do we have? And what are they? Not how many total numbers, just how many digits. The digits are the things, the little things like a 5 that we build all our numbers with. But we build all our numbers with this small group of digits. And what are those digits and how many are there? Or start naming
10.
them for me. Yeah, very good. There's 10. A lot of people say 9 because they forget the 0, but it's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that's 10 digits. And we use those 10 digits to do all kinds of math. And we get to numbers that are bigger than 9 by having the place have value. You know, the ones place, the 10 spot, the columns in a number. When we write 293, that 9 is in that second spot. So we know that doesn't stand for just 9 anymore. It stands for 90. And this 2 is over here. So that stands for 200. So we get 293. But we built all of that, which is 10 simple digits. So when we're picking out a pin, each one of these digits, each one of these little spots that's taken up has 10 possibilities. Our first number in our pin can be any of 10 digits. It can be a 0 through a 9. Same thing for the second one. Same thing for this one. Same thing for this one. So if I multiplied all those together, 10 to the 4th power, there are 10,000 possible pins. Not a whole heck of a lot, but it's just another layer of security. Any more security is built with just multiple layers. Because before, if somebody has my pin, that's great, but they also need my phone. You know, so there's different layers of security. And if they just have my phone, well, then they need to start guessing, and that's really going to slow them down. And it probably freezes after so many guesses, makes them wait a long time. So they use layers sometimes of simple security to build a pretty strong security over the whole thing. Now, this can be manipulated by, sometimes they'll say, well, the first digit can't be a 0. And you probably noticed that with phone numbers. Phone numbers never start with a 0. Do you know why that is? You're probably not old enough to remember to know why that is. But I am, unfortunately. Back in the day, when when we were dialing and pushing buttons on a hardline phone, if you pushed a 0 before anything else, it automatically routed you to the operator. And that was a real person back then who picked up the phone, and you could ask the operator, could I get the number for Ivana House in South Hill, Virginia? And they would look it up and give you the phone number. They were very helpful.
They
So,
can do that.
That's
Yeah.
so crazy.
they did. Yeah, they did at one time. Because of course we had phone books, big old white pages and yellow pages that had everybody's number in it anyway. But they would do that for you. And then as things advanced, sometimes they could put you straight through. Used to be they would just give you the number and you had to write it down, hang up, and then dial it. But then they would have a service for 50 cents more. They'll connect you. You know, they were always making a nickel and dime wherever they could. And yeah, it was pretty crazy because you could also ask for business ones at one time. Give me a number. Is there a McDonald's in Lawrenceville? You know, and a real person would actually look that up and tell you. So
Oh my gosh.
I know it's funny to think about now because when you can talk to a
Yeah,
real
it's like helpful but weird.
I know. I'd be scared to answer my phone.
Right?
it was helpful, but to think of it now, it feels really, really weird. You're right. So I think that's why I start out with 0. I mean, that's why we didn't used to start out with zeros. And I guess the systems just have never accommodated it. And they have some other numbers that were reserved. So sometimes you run into things like that. So when you fill in these little boxes, it changes. You know, if none of them are restricted, we get 10,000. But suppose we say first one can't be a 0. Can't be 0. And you may have something weird like has to end with a 1 or a 2. I don't know, I'm just making up something here. So if the first one can't be 0, we don't have 10 choices anymore. We only have 9. But the second digit's not restricted, so we can use one of any of the 10. The third digit, we can use any of the 10. Now the fourth digit has to end with 1 and 2. So that's only 2 choices, only 2 different digits. So it has to end with a 1 or a 2. So this would give us 1,800 possible numbers if we just put those 2 restrictions on it instead of 10,000. Anyway, you get the idea. And you can also see with these how nice it is to be able to count this way, because with 10,000 choices, you wouldn't want to have to write all those down and then count them and see what all 10,000 were. If all you need to know was how many, that there are 10,000. Who cares what they look like? If I only need to know how many, I'll do it this way and come up with that really quickly. So let's look at some of the examples. Have just a few on this practice thing. I remember seeing. There's going. Hey, don't time out on me. All right. Let's try going back in this thing. No, hope we're not having a Canvas issue. Maybe not. Hold on Canvas just for an hour. No.
Should I check if mine's doing that too? Just
If
to
you
see.
can.
Okay,
Yeah.
I'll check.
My connection here at home is pretty reliable, but it doesn't look like that kind of mistake.
I'll check mine right now.
All right. Take your time. Let's see.
Mine's doing the same thing. It says fail to. Oh, I just muted myself. It says fail to connect.
That's not good. That's going to stop us in our tracks. Let me see if we got an email about this. I don't see. Anything. But since it just started happening, they may not.
You may have to keep like reloading the page
Yeah,
until it
mine's.
works, because every time I get on like Canvas to do my schoolwork, it crashes. Because I always call like tech support, and that's what they tell me, like just wait it out until it.
Okay.
Mine, yeah, mine is working now.
Okay, good. Let's do that. Hey, look at that.
Yay.
You fixed it, Mallory. So next time that happens, I'll just call you and you'll just fix it like that for me.
I feel like I got another question right.
Hey, it's been a good semester. Let's see. All right, we're back on track. Good. I was ready to go today. Have you been hunting yet, Mallory?
No, I haven't. I try to wait till like regular season comes in, which will be after, I think it's the weekend after November 6th.
Oh, is it just bow season now?
Yeah, it's just bow. And I think the 5th and 6th, that's when like muzzleloader comes in and then rifle comes in after that.
Okay. I got you. Yeah, I'd have a hard enough time hitting one with a rifle. I don't need to be out there with a bow.
Yeah, I'm pretty terrible at it, but it's fun.
Yeah. Let's see. I know I saw the couple in here anyway. So we'll find them here in a second. Just hang with me. Here we go. Finally, question 19. Yeah, I think there's 2 at the end here. Yeah, there's only 20 questions. How many different codes of 4 digits are possible? So they did tell us that we're going to use 4 digits. So I like my little boxes. 1 digit, 2 digit, 3 digits, 4 digits. All right. The first digit must be a 3, 4, or 5. So only 3 numbers to choose from there. This one must be a 3, 4, or 5. And it can't end in 0. So if we have 10 digits in our system, and we do, but the first one, we have to eliminate the 3, the 4, and the 5. How many do we have left to choose from for that first digit?
Sorry, can you say that again? I was writing
right.
something.
That's okay. The first digit in our code, of course, we have 10 digits to choose from, but the first digit in our code cannot be a 3, 4, or 5. So how many choices do we have left for that first digit?
Would it be, oh, it wouldn't be 3. Would it be 6?
Close.
Is it 7?
Yes, it's 7 because we have
That's
10.
not the 9-0 part. That's why I was like,
Oh, I
Yeah.
forgot about the 0.
Yeah.
At first I thought it was gonna be the 3, 4, and 5, and I was saying 3, but then I was like, wait, no, that's not right.
Yeah, we're
I don't know why I
taking
thought that.
taking the 3, 4, and 5 out.
Yeah,
So
yeah.
that leaves 7 digits left. Good. All right, now the second digit has no restrictions. So how many choices do we have there?
9.
Close.
Oh, without the 0 still?
Well, no, the 0 is included. 0
10.
to 9 is 10 digits.
Oh my gosh, I forgot there's 10. I was doing 9 again.
That's the most
Sorry.
common mistake. Like that happens a
Sorry.
lot. People think of 9 digits, but we actually have 10 because we include
Yeah.
the 0. All
Yeah,
right, how
I literally, I told you 10 the first time. I don't know why.
about- it's okay. What about this next digit here? How many choices do we have? No restrictions.
10.
There we go. And finally, the 0 has been taken out. So how many do we have to choose from?
9.
There we go. All right. Somebody multiply that out for me and tell me how many total choices we have for this code. Oh, wait a minute. I did something wrong. Sorry.
I was like, I did not have any of that.
Yeah, I did. I'm sorry. I asked the question wrong. It says the first digit must be a 3, 4, or 5. I said it can't be a 3, 4, or 5. It must be one of those 3 numbers. Sorry about that. Sorry a lot. I hate when I do that. So it is 3 choices for the first one. Somebody said that to begin
Oh,
with.
yeah. Yeah.
It said, yeah, that's what it says, but I read it wrong and I told you that those 3 were eliminated. So I apologize for that. But it says it must be a 3, 4, or 5. So
Okay. Well,
that
I
means
got,
we have 3 to choose from.
Yeah, go ahead.
2700.
Yeah.
Me too.
Sorry about that. I hate. Okay, good.
No, that's okay.
Well, it doesn't help when you're trying to show somebody how to do something and you show them wrong.
Hey, everybody makes mistakes.
Yes. But I make at least my share. Not mine. But there it is. There it is. 2,700. Being careful to read next time. All right, here's license plates. And not too long ago in Virginia, our license plates used to be made up of 3 letters, space, 3 numbers. And I suppose they started running short of license plates. So then somewhere along the way, they easily increased the total number of license plates by adding a 4th number. So now we have 3 letters and 4 numbers. And then of course the personalized ones that don't add significantly to the total number. But when they started getting close and started running out of numbers, they thought, well, we'll just stick an extra digit on the end and that'll give us 10 times as many. That increases it by quite a bit. So that's what they did. And that's what they do with phones too. For years, we survived in Virginia, I think on 2 area codes. We had 703 and 804. We might have had the 540 out of Newport News, but now they've added more of those. We have a 434, a 757, so they add more area codes and that gives us more than, more total phone numbers. And I'm sure it's because of mobile phones. Growing up in my family, there was 4 of us. We had 1 phone number. The house phone, that's what everybody had. 1 number for 4 people. Now, we have a family of 5 and we have 6 numbers. We each have a mobile phone and then we still have a home phone. My wife can't quite let go of it. She wanted a phone hanging on the wall in the kitchen.
Oh.
Morally wrong not to have that. So that's what we have. That's the number I give to people when I don't want to have to talk to them. So anyway, license plate, 3 letters, 2 digits. Let me draw my little boxes here. So we're going to build license plates. And I said, well, how about making them 3 letters followed by 2 digits? And Lexi says, well, that's great. But do you know that's going to be enough for everybody in Virginia or not, or for every car in Virginia? I said, well, I didn't think that far down the road. I just thought it sounded nice. So we're going to figure out how many choices that gives us. And let me make some notes on here, do it correctly this time. 3 letters. So this is a letter. Now that's a question we haven't answered yet. How many letters do we have in our alphabet?
26.
Hey, most people don't remember. Don't know
Hey.
that. Yeah, there you go.
I'm a preschool teacher too, so.
Okay, you must be. Usually they struggle with that. No idea how many letters we have. Letter, letter, letter. And then there's no restrictions on the digits. So that's going to give us quite a few because we got a lot of letters. And this is a digit. All right. So you're saying this first spot can be any of 26 letters. Second spot, 26 letters. Third spot, 26 letters. And then what about these last two?
10.
Hey, all right. So if somebody with a calculator, because I'm not going to be able to do this quickly by hand, multiply those 5 things together and tell me how many total license plates we'll have.
I got the third one.
Okay, 1,757,600. So that's a lot of different license plates. So that's how many we would have if we structured them that way.
What was the answer to 19? I was writing and I totally missed it.
That's okay. It is, I think it was 2,700, wasn't it? Well, I did it wrong
Yeah.
once, Mallory, so. be
Yeah, it
glad
was,
you're part
it
of
was 2,700.
Yeah, there it is, 2,700.
Thank you.
And this one right here. So it's nice to be able to count quickly like that, because you'd hate to write all those down. If that was our homework assignment, all right, now go home and write down all the different possibilities. You'd be writing 1.7 million different license plates down. That's no fun. And imagine if you missed one, going back and figuring that out. All right, so that is just a quick and dirty little rule or method on counting the number of atoms in sample space for problems like that. Now let's do our homework. I'm going to let you try a lot of these. All right. If the probability that an event will happen is 0.27, what's the probability that it won't happen? Now this harkens back to, and I didn't mean to click that answer. One thing is wrong, but I accidentally clicked there. That's not the answer, 1.73. This goes back to the complement. You know, if I say there's a 75% chance that something's going to happen, what percent chance it says it's not going to happen? The other 25%.
What?
What's that?
Yeah, it'd be 25%.
Yeah, if I said it was 75% chance that Mallory would get a deer this year, then what would the chance be that she wouldn't get a deer? The other 25%.
So
in
is
this
the
case-
answer 63?
Yeah, very good. So this says, well, close. This says the probability that it's going to happen is 27. So we would just take 1 minus that and get what?
Is it 73?
Yes, it is.
Yeah.
There it is. So it's a 0.73. So that just because we know that the two of those together have to end up to 100%. So if they say it's 27% chance it's not going to happen, what's the chance that it will? Well, the other 73%. So just be careful when you do a problem like that. I hate for you to miss it. Just be careful. Now this is a demonstrating independent events. Flipping a coin is a chance event. Every flip of the coin is independent. It doesn't matter what you just flipped on the one before it. If you tossed it 1,000 times, what's the chance that the 785th toss is a heads? Well, I flipped it 784 times. Now I'm going to flip it the 785th time. I flip it. What's the chance that it's a heads? What's the
Yeah.
chance?
Wouldn't
mean,
it,
Go ahead. I'm
wouldn't
sorry.
wouldn't it be 1/2?
Yeah, because why? Because it's always 1/2,
Yeah,
right?
yeah, yeah.
Yeah. They just threw all those numbers in there to confuse things. The point they're trying to make is flipping a coin is a chance event. And every time we do it, it's independent of all the other times we flipped a coin in our lifetime.
Yeah.
So it's always one half. Always one half. All right, read that one. I got to run to the restroom real quick, sorry, and see what you can come up with there. Let's see. One creative people, good ideas. Okay, 963 inventors in the sample space. And the question is, what's the probability that an inventor has a good idea between 6 a.m. and 12 noon? So correct me if I'm wrong, that looks like these people right here, right?
Yes.
All right, so that is the probability. So that would be my numerator, right? 281.
Mm-hmm.
And what's the denominator?
963.
Yeah, I agree. Now, is that simplified?
No,
Okay, what does it simplify to?
they don't have a common factor.
Oh, so that's as simple as it gets.
Yeah.
Okay, good. So this is what satisfies the condition, and the condition being gets a good idea from 6 to 12. Those are the people, 281, and that's the numerator. And then the denominators are always a total number in the sample space, and that's given up here. So you could do that one again if you had to, right? Yes, you could. I'll answer for you. I have complete confidence in you.
Sorry, yes.
It's okay. It was kind of a rhetorical question. Let's see. Here's another one for you. And there's only not that many on here. 12. We may not get them all done today. We may finish them up Wednesday. John runs a computer software store. He counted 124 people that walked by his store in a day. 52 of them came in the store. Of the 52 who came in the store, only 21 bought something in the store. Estimate the probability that a person who walks by the store will enter the store. Well, the sample space, being careful here, is the people who walk by the store. And how many people walked by the store?
50. Oh, walked by?
Yes.
124.
Okay. That was up here. So that's our sample space, right? Because they wanted the problem.
Yes.
And then they want to know, of those people who walk by the store, how many of those actually entered the store? So the numerator is going to be the number of people that entered the store.
52.
And that's up here. 52 came into the store. So that in this question, the 21 people doesn't even come into play. What does that calculate it to as a decimal?
I got 0.42 when I rounded up.
Okay. Anybody else get that also?
I did.
All right, good. Good job. So just be careful. This one has an extra number in it that didn't get used and some very similar sounding sentences. So be careful that you read closely what they're asking for. A person that walks by the store, that's our sample space. And 124 people walked by the store. And then the number that entered the store, 52 came into the store. So that's our numerator. Okay, a similar one. I'm going to read what they're asking. Estimate the probability of a person who walks by the store will come in and buy something. So we have, if you walk by, will you buy something? So take a few minutes and do that, and then we'll work it together.
Do you want us to just tell you when we have it, or do you want to wait a little bit?
Wait a couple more minutes, and then
Okay.
then I'll get your answer from you. Okay. That's the probability that a person walks by the store will come in and buy something. So what is my denominator? What's the total number in the sample space? How many people walked by the store?
124.
124.
Very good. And then we want to know for the numerator that they bought something. How many
24.
people? Hey, very good.
24. Yeah.
Yeah. Now that we need a little calculator work, but what do you get when you divide 24 by 124?
0.19.
There we go. Very good, both of you. See, this doesn't have to be so bad. And the exciting thing for me is I think you're understanding the concept too. You're not just sticking numbers together. And the concepts, I think, is more important. All right, you're going to draw 2 cards from a deck of cards. And you're going to replace the first card before you draw the second card. What does that make those 2 events? If I take out a card, note that it's a queen or whatever it is, put it back in the deck before I draw the second one, is that second card affected the probability of what that second card is? Is it affected at all by the fact that I took a card out of the deck and put it back in before that?
No.
All right, so what does that make those 2 events?
Independent.
Very good. So what's the answer?
True.
True. Does that make sense? If the second one occurring affected by the first one at all, then they're independent. And it's not affected by the first one at all because after when you drew the card, you stuck it back in. Typically with these card problems, you draw out a card and you hold it in your hand. And that does affect the second one because the deck used to be 52 cards big, but now you got one in your hand, so it's only 51 cards. So those are dependent when you keep the card in your hand because you've reduced the size of the deck for the second draw. In this case, we put it back in, so that made the two events independent. So you said this is true. All right, I'll give you a second to do this one. Then I think, let's see, I might wrap it up on this one. See what the next one looks like. This, yeah, they get kind of different then. So let's just do this one and finish up for the day. And then we'll finish out Wednesday and be ready for our test. You draw 2 cards from a standard deck and replace the first one before drawing the second. Find the probability of drawing a 2 and then a 6. So you want to draw a probability of a 2 and a 6. That's a multiplication rule. And so it's the probability of drawing a 2. Then we put that card back in the deck times the probability of drawing a 6. All right, what is the probability of drawing a 2 out of a deck of cards? How many 2s are there in a deck of cards? Excuse
Four?
me. Yep, there's 4 2s, one in each suit. Over how many cards are in a poker deck?
52.
There we go. So that's the probability of drawing a 2. All right, we drew out a 2, we noted it, but then we replaced it. We put it back in the deck. So how many 6s are in a deck of cards?
4.
4 as well. Now we put that other 2 back in. So how many total cards are in the deck?
52.
Very good. If we didn't put it back in, there would have only been 51, but it told us that we drew it and then replaced it before doing the second one. So this is what we get. 16 over, I don't know, 26 something. Whatever 52 times 52 is. Anyway, if you could just do that multiplication in the
It's-
division.
It's 2,704.
Thank you.
Mhm.
All right, and then what's the division there? What does that come out to? Something very small, I'm sure.
I got 0.0059. Wait, let me do that again because that doesn't look right.
Yeah. Let's just double check that. Sometimes there are mistakes that are not our mistakes. 16 divided by 2704. 0.0059, so 0.006. And we did one like this before. Look at that. That's not one of the answers over here. I need to fix that, don't I?
I guess so.
Yeah, I guess so too, because I feel very confident about this because we did a similar problem on that other practice and we had 0.006 as an answer. So I'll check the test to make sure if there's one like that. There we go, I fixed it.
Yay.
I will fix. Excuse me, I'm gonna fix it right now or else I'll forget. So sorry about this. Let me, question number 7, 0.006. Oh, wait a minute. I just noticed that in either order thing. Let me check one thing. I may have overlooked that. But I could be wrong. Let me check. Yeah, I'm going with our first answer. Yeah, well, we were going to stop here anyway. Let me think about that one a little bit. Just make sure I'm not I'm not overlooking something. Sorry. And what I'm looking at, I need to look at here is this. Yeah, well, let's talk about that one on Wednesday. I'm not going to say that they're wrong because this either order thing that really does change the number of possibilities when we draw the first card. Because if they say you're drawing a card, a 2 and then a 6 in either order, that means when you're drawing that first card, it can be a 2 or a 6, correct?
Yes.
It doesn't have to be a 2 followed by a 6. It could be a 2 or a 6. Well, how many cards are a 2 or a 6? How many possibilities does that give us?
4.
Well, there's 4 2s and there's 4 6s. So that means any of 8 cards will satisfy that first card. All we have to do when we draw the first card is a 2 or a 6. Well, there's 8 cards that are a 2 or a 6. There's 4 2s and there's 4 6s. Does that make sense?
Yes.
All right. Now you've drawn. So Mallory, say you drew a 6. So that satisfies that first card condition. You put it back in the deck. Now that you've drawn a 6, they want to know what's the probability of drawing a 2 and a 6. So now that you've drawn a 6, you have to draw a 2 on the second one. And if you had drawn a 6 first, or if you had drawn a 2 first, then you'd have to draw a 6 on the second one. So that reduces the number on the second draw to how many? They don't want you to draw another 6. Let me draw my little pictures here. Okay, here's my 2 of hearts, my 2 of clubs, 2 of spades, and 2 of diamonds. Okay, that's the different 2s in the deck. Then I have a 6 of hearts, a 6 of clubs, 6 of spades, and the 6 of diamonds. So when I say you can draw a 2 or a 6 in either order, but after you've drawn 2 cards, it has to be one of each. So if Mallory drew, so you can see why there's 8. There's 8 different cards that satisfy the condition of a 2 or a 6. Say Mallory drew the 6 of diamonds on the first draw. Now she shuffles it back in, but now that she drew a 6, the second card has to be a 2. Because at the end of the day, she needs 1 6 and 1 2. So how many 2s are there?
4.
Right. So that's what makes this 4. Because once she drew a 6, then you drawing another 6 doesn't count. You have to draw a 6 and then a 2, or a 2 and then a 6. So you have 8 possibilities for the first card, only 4 for the second. So think about that one for a while. But that gives us 32 out of 2706, 2704. And what does that come out to?
If you round up, it would be 0.012.
There we go.
Yeah.
All right, so think about that one some more. But I think that's the way they're saying. When they say in either order, that means I have 8 different cards I could choose the first time around. Once I've chosen that, then the second card, there's only 4 choices left, depending on what the first one was. But if I chose a 2 first, then I have to choose a 6 second. If I chose a 6 first, then I have to choose a 2 second. Either way, I have 8 choices and then 4 choices. So think about that one some more. Go ahead.
I'm kind of confused on how, because I was taking some notes on how you got the 8 and then the 4.
All right. If I say you're going to draw 2 cards, and the first one, and at the end of the day, after you've drawn 2 cards, you need to end up with a 2 of any suit. And then a 6, or a 6 and a 2, either one's fine. They say a 2 and a 6 or a 6 and 2, either order. So when you draw that first card, it can be a 2 or a 6. How many cards are there in a deck of cards that are a 2 or a 6?
8.
That's where this comes from.
Okay.
Now you drew one. So suppose you drew a 2 the first time. If you drew a 2 the first time, then you have to draw one of these the second time, because you need to end up with a 2 and a 6.
Okay. Okay.
If you drew a 6 the first time, then you have to draw a 2 the second time. So that's still only 4. So that's where this came from.
Okay. That makes sense.
That's a little tricky, so be careful. But the question on the test will be very similar to this. So you've seen
Okay.
it before, so just be careful when you get to this one. If it
Okay.
says either order, think of it one card at a time. Anyway, we could talk about it a little more on Wednesday, and we'll finish this up, the practice or the homework here. And that should prepare you for the test completely.
Thank you.
So, all right, so I will see. Thanks all for coming today. As always, you're great about that. And I will see you all on Wednesday.
Okay. Thank you. See ya.
All right.
Thank you.
Okay.
Bye, everyone.
Bye.